Hey, what are you up to? I am actually in class right now, but I'm the only person in class. So if you are interested in doing what I'm doing, which is teaching myself about the new air-fuel sensors, also known as wideband oxygen sensors, so that you can keep up with the latest automotive technology and help improve your evidence-based diagnostic skills so you don't become one of those asshat parts changers that honestly couldn't diagnose a diaper rash, then maybe you should pull up a seat and join me and we can learn this stuff together. So come on. Yeah, excellent. Make yourself at home. Here, have a soda. So if you are anything like me, and my condolences if you are, then like any other Shadetree mechanic or home mechanic or serious hobbyist or whatever, you are self-taught. And that can be kind of a problem because we don't get to go to automotive technical schools or go to ongoing dealership technician training programs, things like that. We generally have to rely on our own sources for information, including, unfortunately, in many cases, the internet, which I try to use as seldom as possible. I mostly like to use my library up here. And this is just a collection of a bunch of the books and manuals and even a whole bunch of notes that I've taken over the maybe 7 years or so. I've been doing this as a hobby and to kind of make money on the weekends occasionally. But there are a couple of things that I highly recommend you get if you are going to work on your own car. And that would be these. These are actual factory service manuals for specific makes and actually model years of particular cars, and they will talk about everything you ever could possibly know about everything technical and troubleshooting charts and all that. So if you plan on exclusively working on your own car and really never wanting to take it to a shop or anything, it might be advisable for you to find one of those. You can get them on eBay and things. Now, most of my library up here is fairly outdated. I think the newest model year that I cover is a 2003 or so. And that means I have to unfortunately rely on the internet. But I, of course, never use those chat rooms where a bunch of people that honestly I wouldn't let them fix a sandwich, much less fix my car, are going to give advice. What I've got here are several articles from some Toyota engineers who developed their air fuel sensors. And also I've got a couple from Wells Engineering that, as you probably know, is a company that makes a lot of automotive sensors. So I figure these will be reliable sources. And what I'm going to do for my self-training is what I always do. I compile this information, I try to make sense of it, and then I'm going to apply it to an actual application in an actual car to do a few things because I set goals for my training. The first goal is to make sure that I have a thorough understanding of the technology, in this case, a thorough understanding of air fuel sensors, or as I'll use interchangeably, wideband oxygen sensors, why cars have them, how they work, how to read them, things like that. The other goal that I have is I want to be able to diagnose if I have a faulty air fuel sensor or malfunctioning sensor in some way. And then the final goal is to hopefully take the knowledge to another level, which I often try to do, and that is see if I can come up with ways to improve my diagnostic capability by using the sensor as a tool because of my understanding of what feedback I expect from it given certain engine parameters. So in this video, we're going to try to cover all of those today. So if you're still interested and that sounds like it's up your alley, let's get started. Excellent. I see you are getting more comfortable, or I should say more interested in the material. If you're getting more comfortable this up close, then it's making me uncomfortable. But before we begin, I want to make three really quick caveats to this video. The first one is, as I said, I am also learning about these while making this video. This is part of my training that we're doing here. So you will have to take some of the information with a little bit of a grain of salt while I take every effort to, as I said, use multiple reliable sources for the information and compile it and everything. I don't want to also be one of those people I just complained about where they talk out of their ass and they give false information on the internet. I definitely don't want to be associated like that. So the difference is, of course, we are going to validate this information on an actual application to make sure that the information is accurate. But again, I may say some things that may not necessarily be correct because I too am learning this. The second thing that I wanted to point out as sort of a caveat is you are going to need, in order to understand the concepts in this video, a fairly strong understanding of oxygen sensors, your traditional oxygen sensors, like your zirconia-based oxygen sensors. If you do not, then this video is likely to be even more boring than it already will probably be. But if you are still interested in this, then what I recommend is I'm going to put a link in the description to another video I made recently about understanding fuel trims and using fuel trims in diagnosis. It talks in great detail about the function of oxygen sensors and stoichiometry and all of these things that I'm going to use pretty heavily here, so that because most people like me, if you're watching this video, you're going to be more familiar with oxygen sensors than anything else, and I'm using that as the comparison to help with the understanding of air fuel sensors. So if you don't have a good understanding of oxygen sensors, you may want to do that before watching the video. The final little caveat that I wanted to make is, unlike oxygen sensors, which for the overwhelming most part, there's just another exception that's very rare, but for the overwhelming most part, if you understand an oxygen sensor, they're all the same in all years, all makes, all models. But air fuel sensors are not standardized nearly so much. So the figures that I give as far as actual numerical information and things like that is going to vary widely between manufacturers, between models, even between model years. There really is very little standardization, it seems, both from what I've seen personally and in what I'm reading. So the point of it is there will be general similarities, but the idea is you'll have to take this information, maybe experiment on your own car, because if you look at the numbers that I give you and compare them with your car and go, oh, these numbers don't match, do not make a diagnosis that you have a problem with your air fuel sensor then, because it doesn't work that way. So with that said, let's go ahead and get started. And the first thing we're going to do is a very brief review of oxygen sensors and then compare them with how air fuel sensors are different. And once again, I will use, of course, my amazing artistic abilities in this exercise. Always go with your strengths. But I do hope one day that the board here becomes kind of an icon on the internet for Shadetree mechanic training and get some cool name like the Dry Erase Board of Knowledge or something like that. But anyway, you hopefully are very familiar with this trace here, which would be your oxygen sensor trace, which is going to be the same on all oxygen sensors. And again, with one exception, for a very brief period of time, they used these kinky oxygen sensors. What were they? Titanium dioxide or something, where they're a little bit more potentiometric in their theory. So instead of voltages, which are shown here, it used what did it use? Resistance in response to stoichiometric changes. But for the most part, I believe everybody watching this video should be familiar with this. So you've got your stoichiometric line at 450 millivolts and an oscillation changing rich or lean as intended by the PCM between 900 and 100 millivolts. And we know that in rich condition, you have less oxygen detected by the sensor, so there's nothing inhibiting the voltage, so you get maximum voltage under a rich condition, and a lean condition is reported with lower voltages by the sensor. And this again is going to be universal for pretty much any sensor, every model, every year, and everything. Now, the thing is that we're very familiar with this trace and everything. So the first time that you run into an air fuel sensor, I know this was the case for me indeed, and you see a fairly flat line, actually a perfectly flat line at somewhere around 3 volts or so, it becomes kind of an interesting day, because of course your first thought is there is something severely wrong with this oxygen sensor, in that I'm getting 3 volts from a system that should be oscillating between 100 and 900 millivolts, but here I've got a straight line at 3 volts, and it seems like nothing you can do in generating richer lean conditions changes this, and you would almost certainly think you need a new oxygen sensor, and of course that would be a very expensive mistake because oxygen sensors are considerably less expensive than air fuel sensors. And hopefully when you go to the parts store and you find out that it's an air fuel sensor, you stop and maybe rethink it a little bit. But this actually is the new normal for a engine in stoichiometry, is this flat line. And the thing that, there's a couple things that make this a little tricky. Actually, there's a lot of them, so you kind of have to stay with me here. One of them is these voltages. These voltages that represent the stoichiometric line, as I said, are not standardized. They're different for different models, different makes, even different model years. So what we're going to do for most of this exercise is, because Toyota was one of the earlier models to use or makes to use air fuel sensors, we're going to do 3.3 volts because most Toyotas you're going to see that, and I assume that because these are older type sensors that there's more of them out there, so there's a better chance that your air fuel sensor is going to match this up. But keep in mind that this 3.3 volts may not be the same in your application, but this is your new normal. Now, there's other things to get used to as well. And one of those is, as you hopefully know, if you were to have a rich condition with an oxygen sensor, let's say that you add propane to the intake, then what's going to happen is, in the absence of oxygen that is displaced by the propane, remember oxygen sensors only read oxygen. They have no idea that fuel exists. If you were to cause a misfire by pulling a spark plug wire on a cylinder, the unburned air and fuel that passes through would actually cause a lean condition on an oxygen sensor. Why? Because the oxygen sensor doesn't see that unburned fuel. It sees the unburned oxygen, which would be much higher than normal from a burn cylinder, so it detects a lean condition. That's how an oxygen sensor works. Air fuel sensors are different. We'll talk about that. But if you were to create, say, a rich condition by adding propane to the intake or something, you would be well familiar that you would get this rich line on your oxygen sensor. Well, air fuel sensors report kind of backwards. What would happen if you were to add propane to an air fuel sensor is you will actually get, let's say 2 volts here and let's say 4 volts here. And again, these numbers don't mean anything. Actually, they really don't mean anything because the voltages are imaginary. I'll talk about that in a minute. But what would happen is you would actually start, of course, going rich. The air fuel sensor does the same as an oxygen sensor, just reports the variance from stoichiometry, but it's going to reduce voltage at a rich condition. So in this situation with your air fuel sensor, you would be rich. And conversely, as you know, if you were to, say, pull a vacuum line or something from the intake, and you would cause a lean condition and your oxygen sensor would start leaning out. Again, same thing with an air fuel sensor. It's going to detect a lean condition, but as you can probably predict now, it's going to report that lean condition with a higher voltage. So this is lean. So as you can see, the reporting from an air fuel sensor is sort of backwards from that of the traditional oxygen sensor. So this is another thing now that you really kind of have to get used to. And it's kind of tricky to get used to, and I apologize in the video if I make some Freudian slips because I've spent 7 years doing this and 7 minutes doing this now, but we'll do the best we can. Now, I did mention a second ago that these voltages are imaginary. So let's look a little bit more into the inner workings of the air fuel sensor and get a better understanding of the differences here. So as you know, and as I just described, an oxygen sensor measures oxygen, and it does it through voltage. We know this. The air fuel sensor, and you may see many different names for this: air fuel sensor, wideband sensor, constant lambda sensor, all kinds of stuff. May have different names on your scan tool even, but it actually uses current to measure the actual air-fuel ratio. So unlike the oxygen sensor, it doesn't simply measure oxygen in the exhaust, it actually measures the ratio of air to fuel, and it does it using current instead of voltage. However, it uses very, very, very minimal currents, and it also does it through polarity change. So let's kind of examine that a little more thoroughly. Again, with our air-fuel sensor, we're going to have, let's again use our Toyota example. So we're going to have stoichiometry and a good running engine at 3.3 volts. And here's our scale here. And at stoichiometry, there is going to be no current, no amperage. Remember, this is current, not voltage now. There is going to be no current through the sensor at stoichiometry. This is how the PCM knows that the engine is in stoichiometry. There is no current detected. Now, in a lean condition, and I admit I'm pausing right now because I'm trying to think backwards here, but in a lean condition, we're going to see an increase in this voltage. But what is actually happening is there is now amperage being put through, and it's going to be in a positive polarity. Conversely, if we were to say add propane to the intake or whatever, and we start going rich and bringing it down here, well, what that's going to be is a very minuscule current change, but this time it will be in the negative polarity. And that is going to be a problem that I'll describe later on with these really small amperages. But this is how the air-fuel sensor is vastly different than an oxygen sensor, because you can kind of think of the air-fuel sensor not so much as a battery that is inhibited by oxygen like I usually think of an oxygen sensor, but with an air-fuel sensor, it's sort of like a mini polarity changer kind of thing. But there's also other differences with this too, in that the air-fuel sensor is more quantitative than an oxygen sensor. It actually is better at measuring the air-fuel ratio, and we'll talk about that in a second. But another major difference is these voltages here actually do not exist. They're just simply interpreted data that is given for the purposes of the scan tool based on the low current and polarity information. So these are actually just interpreted values. There really isn't actually a voltage change on this. And we'll talk a little bit more about that on diagnosing the wideband sensors. So let's talk another thing about a question you might have, and that is, why do we even have to have these air-fuel sensors in the first place? Why do I have to have this straight line now as stoichiometry instead of my usual oscillation? And now I've got to think backwards on my rich and lean conditions. Well, the reason is because of emissions requirements. And let's take a look once again at the familiar oxygen sensor here. And of course, we're very well familiar with this, but this isn't actually how the data is given to the PCM. It almost looks as if there are degrees of leanness and richness here, so that at 450 we know that we would be at stoichiometry, but if we were at say 600 millivolts, we would be a little bit rich, and maybe at 250 millivolts we would be maybe a little bit lean. It actually doesn't work that way. When you look at what the PCM sees from an O2 sensor, it doesn't look so much like this. It looks kind of more like this. And there's a very narrow range here at stoichiometry, such that if you notice, the PCM can only see the oxygen sensor reporting either rich or lean, but it cannot tell how much it's rich or lean. It doesn't have like a dynamic capability to determine richness or leanness. And because it only has this narrow sensing of the stoichiometry, that's why you've probably heard of a regular oxygen sensor often being called a narrow band oxygen sensor. Now, let's converse this with your air fuel sensor. So your air fuel sensor, again, not measuring oxygen, but actually measuring the ratio of air to fuel, it is going to have a much broader capability and a lot better dynamic range. So if we have, say, stoichiometry, and then we go lean and then rich, well, it actually can detect the degrees of that. So its range is much broader, and that is why this is known as a wide range oxygen sensor. And this is going to be far better at determining the fuel trim, at optimizing the catalytic converter, and at basically controlling emissions. So if you have a very, very low emission vehicle, this is going to be the way to go over an oxygen sensor. Needless to say, that is the trend in the industry and with requirements from the EPA and such. So we are going to see air fuel sensors considerably more and more. All right, so now that we have a fairly decent understanding of how the air fuel sensors function and why we need them and what they do, what their responsibilities are. The responsibilities are the same as an oxygen sensor. Let's start talking about how to diagnose if you have a problem with an air fuel sensor. So one of the things that we know to do with an oxygen sensor is we can induce conditions where we know that a functioning oxygen sensor is going to behave a certain way. And we can measure this using a scan tool, or actually even an oscilloscope, or actually even a regular digital volt-ohm meter. You actually can do that. You are not going to be able to do that, however, with a air fuel sensor. You are going to need a scan tool, and I'm going to explain why, because you're never going to be able to diagnose an air fuel sensor unless you've got the right equipment. And this, unfortunately, could be kind of a demise for a lot of Shadetree mechanics, similar to how when we got electronic computer control and fuel injection and oxygen sensors, it kind of killed off a lot of the Shadetree mechanics from the 70s. Well, you know, now if you've got to invest in scan tool equipment and learn how to use it in order to diagnose vehicles, this could be a problem. But one of the things we know is, first and foremost, being able to detect this trace. When we detect this trace on an oxygen sensor, we know the oxygen sensor is certainly working. We can even further test it because if we were to, say, add propane to the intake, we know, as described, that we would get a rich condition, and if we were to cause some kind of vacuum leak or lean condition, we would see the voltage dropping in an oxygen sensor. So we can kind of control it, and we can measure that change. Well, the thing is, with an air fuel sensor, you are not going to be able to do that using a digital volt-ohm meter. You can create changes in the sensor output based on changing the conditions, rich or lean in the engine, but you are not going to be able to measure it through any traditional way. The thing is, with your oxygen sensor, you have reasonable voltage outputs, no less than 100 millivolts, that you can measure, again, with even a digital volt-ohm meter. Now, it's not a pretty way of doing it because DVOM is not designed to catch a moving target like that. It's going to try to take an average reading of that particular moment, but it's always changing. So you're going to get your DVOM changing all the time to, I wish I could draw, to all kinds of different numbers, you know, 0.2, 0.8, 0.7, 0.6. But the thing is, if you follow your DVM enough, you're going to see that it is indeed creating some type of oscillation pattern. And of course, if you create a rich condition, it's going to kind of fairly stabilize. It's still going to be a little jumpy, but your DVOM will fairly stabilize at either a rich or lean condition if it's held. But you can do these measurements if you don't have really good equipment. It's really much better to use a graphing capability. The problem with trying to do this on an air fuel sensor is twofold. with your air fuel sensor, and again, let's use our Toyota example at 3.3 volts stoichiometric, and let's go to 4 and 2 volts. And again, remember, these numbers are going to be insignificant maybe to your car. They could be totally different. At stoichiometry, you're going to measure 3.3 volts, but remember, any changes, either lean or rich, do not reflect in a voltage change. They are milliamperage changes, and we're talking like less than half of a milliamp. So the first thing, you can't measure voltage. There will not be a voltage change. These voltage changes don't even exist. They're imaginary. They're just given by the scan tool for the purposes of showing some familiar point of reference. So you can't measure it that way. But your other problem is that your milliamp scale is going to be too low to detect with the DVOM. Well, certainly at least for mine. And I'm actually not really all that familiar with DVOMs on the market. I know mine costs like $30, and I know there's no way it's going to measure anything even close to this. You would have to have one that's capable of measuring amperage, first of all, and then measuring extremely minuscule amounts of amperage. Now, I've seen DVOMs on the market that cost hundreds of dollars that don't even graph or anything like that, and I'm not really sure what the deal is with those. Maybe those are capable of actually measuring minute amounts of current, but even so, if that's the case, and you have to spend hundreds of dollars on one, well, I would argue you're better off buying a really inexpensive scan tool, and you would actually be better off. So that's going to be kind of a problem. You are going to have to invest in some type of dedicated equipment to be able to diagnose the trace on a air fuel sensor. Now, that said, provided that you do have the capability to diagnose your air fuel sensor, you will be able to do like with an oxygen sensor and make predictions. One of the most important things, though, is like an oxygen sensor, make sure that it's fully warmed up before you begin. As you are probably well aware, oxygen sensors don't start functioning until the engine goes into closed loop, that is fully warmed up, as opposed to open loop when a bunch of default parameters are used and everything. But then when the engine warms up, it uses the sensors in the engine, and the oxygen sensors need to be at like 600 or 700 degrees, something like that, before they start functioning. And that's the same thing with a wideband sensor, but wideband sensors operate at a much higher temperature. I think it's something like 1200 degrees, something like that. But before you start doing testing and using your equipment for measuring the output on a air fuel sensor, make sure that it's warmed up. That's really important. Now, one of the things that you are probably familiar with when diagnosing an oxygen sensor is the dead oxygen sensor. So that is the oxygen sensor that is just flatlined, and it can be flatlined either rich or lean. A lot of times it'll be flatlined lean. So this is your 100 and 900, and no matter what you do to this oxygen sensor, you add propane to the intake, you pull a vacuum, whatever, it just doesn't respond. Now, this would be evidence most likely of a bad oxygen sensor, especially if this sensor doesn't respond to propane. If you add propane here and this sensor doesn't start going rich, almost certainly dead oxygen sensor. Now, you can have a failure like this happen in an air fuel sensor too. In an air fuel sensor, what would a dead, non-responding air fuel sensor look like? Well, most certainly it would be stuck at stoichiometry. Why? Because, remember, it's amperage that's measured here, and at stoichiometry, there is no amperage. So you have one of two explanations. If you add propane or you pull a vacuum hose or you try to do something to change this and you cannot get it off of stoichiometric, then what likely is happening is you have an open in the circuit, because remember, there's no current flowing through it, so it's open. Now, that open could be before or in the air fuel sensor, but that's one of the things that you want to look for, is not immediately jump to a bad sensor, but similar to an oxygen sensor, test whether you have other electrical problems. But typically on a air fuel sensor, this is a good indication that you are looking for an open in the system, is if you are stuck at stoichiometry and there's nothing you can do about it. Now, there's another trick that you can do to validate the ability of an O2 sensor to function, and that is, of course, as I said before, add propane, and if you add propane, it should go rich, and if you induce a vacuum leak, it should go lean. So you should see those changes, very similar to testing an oxygen sensor. But there is another way that is actually recommended in this Toyota document that I'm studying here. And according to the Toyota document, what they suggest doing to test the functionality of an air fuel sensor is to use a snap throttle test. And what that means is taking the throttle and wide open throttle all the way for just a second and then let it go. And that is going to give a very characteristic pattern that they're showing here that indicates that the air fuel sensor is working, because doing that snap throttle is going to test the sensor in both directions, lean and rich. So what that's going to look like is